Okay guys, in this video we will continue with the concept of distances to stars, which is part of the topic 11b called space in unit 5. So let us start. So distances to stars. Okay, as we said in the very first video in this topic, all we see from down here on our planet is light that comes from stars. And also, okay, we talked about other particles and so on that come from stars, but let's focus on light. So the biggest question, I guess, is how far away are these stars, okay? And to demonstrate the problem, let's assume, okay, if L, the luminosity, okay, the luminosity of a star is somehow known, okay, is somehow known, okay, then we can measure the intensity of light from that star here on Earth. And I remind you that the intensity of radiation I is measured in watts per square meter. Okay, this is something we can measure. Okay, so if we know the intensity and the luminosity, we can find the distance. Why is that? Because then we can measure the intensity. Give me a minute. Okay, then we can measure the intensity, okay, and find the distance. I'm sorry for mumbling. So let me show you what I mean. Let's say that there is a star over here. Maybe it's in the Alpha Centauri cluster. Maybe it's in some other cluster, etc. But we know the luminosity. Okay, the luminosity is given in watts, right? And here we are, here on Earth. So this is our planet. A dot compared to the star, and of course, I mean, we're talking about massive distances. So yeah, I mean, yeah, I mean, things appear like dots, even stars appear like dots from a huge distance. So okay, this is the distance we want to determine. Okay, this is D. The star emits light radially outwards, and radially means like in spheres, right? Okay. Okay, so this is where we measure I, okay? And I, the intensity, is given by the radiation law, the inverse square law. I is equal to the luminosity over 4 pi d squared. Why 4 pi d squared? Because this thing over here that I show is a sphere, right? And the surface area of a sphere is 4 pi d squared. And why d squared? Because the star is a distance of d away from us. So you can imagine a large sphere of surface area 4 pi d squared, where the luminosity, the total light output of the star, is distributed evenly around this sphere, okay? Therefore, the intensity is L over 4 pi d squared, okay? So if we know L, and if we measure I, we can simply solve for D to find, okay, 4 pi d squared is L over I. So D is the square root of L over 4 pi I. Okay, and let's do a quick example. If the luminosity of the sun is L equal to 3.8 times 10 to the 26 watts, then what is d, the distance, if the measured intensity of radiation here on Earth is 1300 watts per square meter. Okay, so we will just plug into this formula over here. So d is simply the square root of 3.8 times 10 to the 26 watts over 1300 watts per square meter. So watts cancel, and don't forget the 4 pi, I almost forgot. Okay, so if we do that, we find 1.53 times 10 to the 11 meters, which is also known as 1 astronomical unit, which is something we will talk about next. But it just occurred to me that it is well known that the light from the sun takes 7 minutes to reach our planet. So let's actually calculate the distance that way and compare. So speed is distance per time, right? And here we're talking about the speed of light. So the velocity is c, I'm sorry. So d is 3 times 10 to the 8 meters per second for the light. Wait, I messed up something. Yeah, d is ct. So okay, d is ct. Therefore, d is that times 7 minutes, and 1 minute has 60 seconds. So I have to multiply by 60. So this cancels, and I have my calculator here. Let's do this calculation. 3 times 10 to the 8 times 7 times 60 gives us 1.26 times 10 to the 11 meters. Okay, why do we have a discrepancy? Okay, it's the same order of magnitude, which is good. So 10 to the 11 in both cases. And I guess the time is not exactly 7 minutes, maybe it's a little bit more. So I don't know the exact calculation. So this is something that's good to do in physics, to cross-check calculations and results and so on. All right. So I hope the problem is clear. Like, it's important to know how far away a star is from us, but to do that, you need to know the luminosity. Therefore, we have to rely on other techniques as well to find that distance, okay? Because the luminosity is not something that is very well known for everything out there, right? Now, before we move on, it's good to talk about units, or yeah, I guess units is a good way to put it. Units that are used to measure astronomical distances, okay? So using meters to measure astronomical distances is inconvenient, okay? Inconvenient. Therefore, we need larger measuring sticks, I guess. So just to give you an idea, the distance between the Earth and the Moon, so the distance to the Moon is 400 million meters, okay? The distance to the Sun is something we just calculated, and it's 150 billion meters away. So okay, this is thousands, this is millions, and this is billions. Okay, just checking to make sure. And you see how I put the zeros, every 3 zeros have a space between them just to help me see what's going on. But it's convenient to define. Let's start with that. 1 astronomical unit, okay, is 1.5 times 10 to the 11 meters, which is the distance to the Sun, okay? So the distance to the Sun is 1 astronomical unit, okay? The next useful distance is the light year, okay, light year, which is something you're familiar with, I'm pretty sure, from sci-fi movies, sci-fi novels. Sometimes it appears in the news, documentaries, and so on. So this is the distance light covers in 1 year. So to find that, we multiply the speed of light, which is 3 times 10 to the 8 meters per second, times 365.25 actually is the exact number, days in a year, times 24 hours, days in a year, yeah, times 24 hours in a day, times 60 minutes in an hour, times 60 seconds. Times 60, wait, I'm confused. So 24 hours, 60 minutes in an hour, 60 seconds in a minute. Yes, okay. So that's seconds, this cancels. And if we do the calculation, we find 9.46 times 10 to the 15 meters. So 1 light year, this is how you write it. You don't need the dot in front of the oops. So 1 light year, okay, is equal to 9.46 times 10 to the 15 meters. Let's box the astronomical unit, then let's box the light year. Okay, now let's talk a little bit about angles. Okay, okay, here. So angles, what do I mean by that? So if I have an object over here, I guess, okay, and I'm standing very close to it, this angle theta is quite large. It's quite large. Maybe it's 5 degrees, maybe it's 30 degrees, something like that. But if I'm standing over here and an object is 5 light years away from me, then this angle is really tiny, okay? So this is the angle I'm interested in. So measuring it in degrees doesn't make sense, because a degree is a large unit to measure very, very small angles. So we use the arcminute, okay? One arcminute is defined as 1/60th of 1 degree. So that's 1/60 of a degree. It's also denoted as 1 and then the script there, which is like the minute, okay? So 1 minute. And then we also define the 1 arcsecond, and by now you should suspect that that's 1/60th of the 1/60th of 1 degree, okay? So it's 1/60th of 1 minute, of 1 arcminute. So that's 1/3600 of a degree, and it's denoted by a double script, okay? And these are useful to something we will talk about now, okay? In a method actually that we will talk about now called parallax. Okay, so what is parallax? So observe, one way to measure the distance to a star is to observe how a star's position changes with respect to a background of other stars, to a background of other stars. Let's see. So you observe a star's position, how a star position changes with respect to a background of other stars, which remains stable. That's important, okay? Which remains stable in the sky. And this will make more sense if we find a good picture that demonstrates this. So let's go to the European Space Agency website. And okay, they have a video. I hope I don't violate any copyright laws, but it's for, if anybody at the European Space Agency is listening to this video, please, I mean, forgive me. I mean, it's this for educational purposes, I guess. So let's watch the video. Okay, so you see, what do they show here? Okay, they show, I guess, what happens within a year. So you see how some stars move in the night sky. And why do they appear to move? Because they are closer to us. Whereas, okay, let's go back to the notes. So what's happening is that some stars appear to move in the sky because they are close to us, okay? If they are really, really far away, even if they move, we won't notice it, okay? So to demonstrate this, let's start with the sun, okay? So this is our sun. And this is the Earth, okay? 6 months from now, the Earth will make it all the way around over here, okay? What is this distance? It's 1 astronomical unit, right? Same goes for this distance. So because, okay, and yeah, this is in 6 months. Okay, let's say that there is a star all the way over here, okay? Actually, let me move it a little bit. Okay, this is my star. And this is the background of other stars, okay? So these are stable stars. What do I mean by stable? If I'm standing over here on Earth, observing these stars, the stable stars, now and in 6 months, okay, they will not change position in the sky. But this guy will, okay? So if this guy's distance is d, okay, if we are standing over here now and we observe this star over here, then behind it we will see these stars over here, right? But if we observe the same star in 6 months, our perspective will change. So behind it we will now see these stars, okay? And again, these stars in the background do not change position, but this guy will change position, okay? And all we have to do is to measure this angle. This is done with specialized methods that not the European, I mean, the European Space Agency, the NASA, and all these guys, they have ways. They take pictures and they compare pictures against each other and they figure out this angle theta, okay? But you don't have to worry about that. At this level, the A level, this is going to be given to you. And that's that angle theta, actually 2 theta, both of these angles together, is the parallax, okay? I hope all this makes sense. So the parallax is defined as 2 theta, okay? This is a definition. So if we know that theta, all you have to do is to use trigonometry to find the distance to the star, because tangent of theta is about, if we use this triangle over here, this triangle over here, and this is theta, then the tangent of theta is 1 astronomical unit over the distance we are interested in. And if an angle is really, really small, then the tangent of theta is approximately equal to the sine of theta, and that's approximately equal to theta. So theta is 1 astronomical unit over d. Simple as that. Okay, let's work with an example. My favorite star, I guess, because I keep mentioning it for Alpha Centauri. the parallax, oops, is 1.52 seconds. How far away is it? All right, so the parallax is defined as 2 theta. So 2 theta is 1.52 seconds, right? So theta is simply 0.76 seconds, which is equal to 0.76. 1 second is 1 over 3,600 of a degree. So that's simply 2.11 times 10 to the negative 4 degrees. And since tangent of theta is 1 astronomical unit over d, then d is 1 astronomical unit over the tangent of 2.11 times 10 to the negative 4. So d is 271,544 astronomical units. Okay, that's far away. All right, what else do I want to talk about? Let me see. Okay, it's important. Okay, I found what bothers me. Theta is demonstrated here and here and here and over here, obviously in the calculation, has to be expressed in degrees. Okay, now let's go see another thing that is important. The parsec, which is another unit of distance in the universe, the parsec, which is which stands for parallax second, is defined as follows. If theta is 1 second, which is 1 over 3,600 of a degree, then tangent of theta, oops, sorry, I'm still learning how to use this. Then the tangent of theta is 1 astronomical unit over d. So d is 1 AU over the tangent of 1 over 3,600, which is equal to 3.09 times 10 to the 16 meters. So 1 parallax second, or 1 parsec, 1 parsec is equal to 3.09 times 10 to the 16 meters. All right? Now, if theta is given in arcseconds, you can use theta in arcsec to find the distance in parsec. So what I mean by that is if you just use theta as is given to you in arcseconds, you can directly calculate the distance, and that distance is automatically going to be given in parsecs. So to get distance in parsecs, as d is 1 over theta, and this is going to be in parsecs if theta is in arc seconds. So for example, for Alpha Centauri, theta is 0.76 seconds. So d is 1 over 0.76, which is 1.32 parsecs. Okay? And parsecs is also written as PC. And that's it, I guess. So you can either convert this angle, the parallax angle, if it's given to you in arcseconds or arcminutes, you convert it to degrees, and then you take the tangent of that angle to calculate the distance in meters. Or you can directly use theta in seconds to calculate distance, and that distance is going to be in parsecs. Okay? And this is it for this parallax method. It's important to note that the parallax method works up to a few parsecs, usually up to 30 parsecs, since at some point theta is way too small to be noticeable. In other words, the star is so far away from us that despite observing that star now and in 6 months, we will see it, we will find it to appear in the same exact position. And that's because it's so far away that there is no parallax anymore. I hope that makes sense, okay? So this is for the parallax method here on Earth. For orbiting telescopes, okay, for orbiting telescopes, we can measure angles. Sorry, that was my sister calling. We can measure angles down to 24 micro arcseconds, or d is 1 over 24 times 10 to the negative 6, because 1 micro arc second is 10 to the minus 6 arc seconds. So that's why I wrote that down. So that's 41,667 parsecs, or in light years, that's actually, let me write it down here, or 136,250 light years. Okay, and yeah, you see how we can measure the distance to stars. But oh, I forgot to mention that about 100,000 light years is the diameter of the Milky Way, for example, our galaxy. Okay, so within our galaxy, the parallax method works kind of for stars that are close to us. For stars that are really far away, you can use an orbiting telescope. Those are telescopes that NASA puts in orbit around the Earth. I'm not aware of other space agencies. They might have their own orbiting telescopes. But anyway, this method works as far as the star is kind of near. Okay. Now, what do you do if the star is far away? We will talk about that next. Okay, a second way to measure the distances to stars is by using the so-called standard candles. So let me switch on the air conditioning because it's really hot where I am. So What do you mean by that? So first of all, recall that the intensity of radiation that we measure at a distance d from a source is given by the luminosity over 4 pi times the distance squared. Okay, so this intensity of the radiation we receive from a star can be measured. Okay. Now, so theoretically, if we know this luminosity, if that luminosity is known, then we just have to measure the intensity and then we can automatically find the distance. We already discussed this, of course. So it turns out that standard candles are types of stars for which the luminosity is known. Okay, so for some types, of stars, such as the type, the type 1 supernova that we discussed about in the previous video. So type 1 supernova and others. Okay, L or the luminosity is always the same. Anywhere they are in the universe. Thus, if one is found, its luminosity is automatically known. Okay, and one important thing to note here is that the luminosity refers to the luminosity of the star. Therefore, standard candles were observed nearby initially. Okay, so let's say that there was a type 1 supernova, I don't know, 10 parsecs away from here. If it was 10 parsecs, then people were able to find the distance using the parallax method. And once you know the distance, and because you can measure the intensity, you automatically find the luminosity. Okay, so if you find the luminosity for one such standard candle, then you know the luminosity of any other standard candle in the universe. So if a standard candle is observed 100,000 light years from here, for which the parallax method cannot really be used, then you can find the distance using this formula over here. I hope this makes sense. So actually, let me write it down. So note L, the luminosity of a standard candle, is initially determined using the parallax method. For a nearby star. Okay, so so I'm mentioning this because here on Earth we can only measure the intensity of the light we receive from a source. Okay, now let's go see an example. For Betelgeuse, the luminosity is 5.4 times 10 to the 30 watts. Okay, the intensity of radiation is 1.1 times 10 to the minus 8 watts per square meter. That's tiny, actually. Thus, its distance from us is the square root of L over 4 pi times the intensity, which is 6.25 times 10 to the 8 meters, and expressed in light years, that's 660 light years. Okay? So that was the second method. Let's go see a more advanced method, okay? Let's go talk about Cepheids. Cepheids, or variable stars. Okay, so these are stars that pulsate with time. So they do a motion like this, okay? They pulsate, meaning that they oscillate, so their outer layer expands and contracts at all times, meaning that the intensity of radiation we see from this star varies with time in a periodic manner, okay? So if we plot the intensity of radiation versus time, we will see something like this, okay? So now let's go talk about Mrs. Leavitt, who discovered this. She was a great astronomer, I think at Harvard about 100 years ago, who studied variable stars pretty much and other things. So Leavitt found that I actually just got an idea right now that maybe in the future I should make videos with biographies of scientists and maybe other people as well, because it's kind of fascinating to read the story behind certain characters and figures from history and science. So Leavitt found that for some stars, she was working with a nearby galaxy. Actually, it's two galaxies, the small Magellanic Cloud and the large Magellanic Cloud, I think they are called. These are galaxies that orbit our galaxy. So she studied that, okay? So Leavitt found that for some stars, the intensity of radiation received from the star here on Earth oscillated over time with a constant period of about 1 to 50 days. Okay, so if you measured this intensity given in watts per square meter versus time, and let's put the time in days. So 0, 1, 2, 3, 4, and so on. She observed something that looked like this, okay? Let's put the average here as a reference. So she observed something like maybe, okay, something like this. It's not the perfect graph, but you get the idea. Okay, these stars were observed in the Magellanic Cloud which is 158,200 light years away. Therefore, all stars can be thought of as being at the same distance from the Earth. Okay. Also, she found that the brightest stars had the longest periods. Okay, so she plotted the luminosity, actually, let's say the intensity of radiation measured from these stars over the intensity of radiation from the sun as a function of the period in days. Okay, so 1, 2, 3, 4, 5. Okay, and what she found was a linear relationship that looked like this. Okay, so if this is say 1 and this is 10 to the minus 2 and this is 10 to the minus 4, then she established that, okay, if I find a variable star with a period of say 2 days, then I sorry, this is 10 to the 2, I'm sorry, this should be 10 to the 2. Okay, so if I find say a star with period of 2 days, I immediately know that its intensity is 5 times the intensity of the sun. Okay, and once I know the intensity and if I establish the luminosity of that star, I can find the distance. Okay, but how would you find the luminosity? You still need that point. That's kind of easy because you can use parallax from nearby pulsating stars. Okay, so by using parallax, actually the parallax method, it's better to put it that way. So by using the parallax method on known pulsating stars nearby, such as the Polaris star, the distance and therefore the luminosities were determined. So what I'm trying to say is that by finding the distance to nearby Cepheid stars in our solar system, say, they were able to establish a graph that looked like this. L over L of the sun versus time in days. Okay, so they were able to establish this plot pretty much, okay? Because it's the luminosity that you need to find distances, right? Because all you measure here on Earth is the intensity of radiation. So for the Magellanic Cloud, she found this, and then using nearby stars, they were able to find the distance from the parallax method, and by using the the measured intensity, they were able to find the luminosity of stars, and therefore we now know that if we find a variable star anywhere in the universe, all you have to do is to come to this plot and say, okay, its period is 5 days, okay, and from those 5 days we can find the luminosity, and once you know the luminosity, all you have to do is to use I equal to L over 4 pi d squared to find the distance. Okay, so Cepheid stars are important in astronomy because they can be used to determine the distances to really far away stars. So Cepheids, I'm going to close with this thought. So Cepheids can be used to find distances, to measure distances up to 10 to the 6 or 10 to the 7 light years. I hope this makes sense. If it doesn't, let me know in the comments. Let me summarize again, because I feel like I kind of lost you a little bit. So let's start with this observation. So Leavitt figured out that there are stars for which the intensity of radiation received from the stars varies with time, with constant period. That's a key. She then found that in the Magellanic Cloud there are many Cepheid stars, and the Magellanic Cloud is so far away that we can assume that the distance of any star in the Magellanic Cloud is at the same distance from the Earth. And she observed that the intensity of radiation from these stars versus the period of pulsation gives you a straight line, okay? Once they knew this, they looked for Cepheid stars in our galaxy and nearby, and pulsating stars for which the parallax method can be used to find their distance, okay? So the distance was found, and once you know the distance, you know the luminosity, okay? And then they converted this graph of intensity to this graph of luminosity, okay? So now you are able to have a plot that told you, okay, if a star has a period of pulsation of 4 days, then the luminosity is that much, okay? And once you know that, you can find the distance using this formula over here, right? And okay, this is it for Cepheid stars. And there is one last method. There are probably other methods as well that professional astronomers use. I have to read the literature and see if there is anything else. But another method to measure the distance to stars is using the Hertzsprung-Russell diagram. So, and this is the last method we will talk about. So other methods, it's the HR diagram. So you can use the spectrum of a star to find the peak wavelength. Okay, then from that peak wavelength, you can use Wien's law, which I'm writing down right now, to find T. Okay, and then once you find the temperature, you can determine so the width of the spectrum actually the width of the spectral lines can tell you whether a star is in the main sequence. If it is, use the HR diagram to read off its L, and then using L and the measured intensity, you can find D using I equal to L over 4 pi d squared. And let's go try to find some examples of this spectra. And by the way, I remind you that the HR diagram looks like this. And the temperature increases to the left. Therefore, if this is 2000, this is 10,000, okay? And you have this line. So once you know the temperature, you can just read off the luminosity you want, all right? And before looking at the internet to find spectra, let's mention that this method works for distances up to and including about 10 to the 5 light years. Okay, let's see. So spectrum of main sequence stars. So this is a good table. I think it's from Wikipedia. Okay, it's the one we used earlier. So you see up top it's a class O star, and you see the spectral lines. You have the helium lines, and the hydrogen lines. Okay, I hope this makes sense. For a class B star, you see how we have the helium lines and carbon lines, and down to class M we have many admixtures because we have I guess many types of elements and molecules included in those stars. But for a comparison, okay, so this is the spectrum of main sequence stars. Okay, so the temperature can be determined, as we said, from Wien's law and the peak lambda, and then you have to look into the spectrum you receive from that star, and it has to look something like this. Let's compare it to the spectrum of let's do red giant stars. Okay, so this is what we mean. This is the spectrum of a white dwarf on the bottom, and you see how the spectral lines are widened because of intense pressure on the surface of the star. Okay, and for a blue giant star, which is in the main sequence, okay, you see how thin those spectral lines are. All right, so I was wrong earlier. No, I wasn't wrong. I just mentioned that you have to see the width of the spectral lines. So if they are so wide, like the ones we see here on the bottom, then we know that that's a white dwarf. It's not in the main sequence, so this method cannot be used. Okay, I hope this makes sense. Let me go back to the notes to close this lecture, this lesson. So yes, I hope this makes sense. Let me know, guys, if these videos are helpful. Like and subscribe, as I say. And I think there is one more video and we are done with Unit 5. Okay.